Hello, Rachel and I were Team 2, the spectroscopic fraction analysis team. The goal of our team was to determine the absolute amount of total protein in each fraction and determine the fractions enriched with MGH. This was done by using the Bradford Blue assay, which uses a standard curve to compare amounts of a standard protein to the fractions containing protein determined by the FPLC team. So this is our standard curve. The Bradford Blue assay measures the amount of blue using the absorbance 595 for Kamasi stained proteins to directly compare the blueness between the samples. The bluer the sample, the more protein you have in your sample. There were two microplates used for this experiment. The first one was for the Bradford Blue assay, which contained the 25 fractions in the 8 standards. And the 8 standards were used to make the standard curve, but you're only seeing 7 data points because we eliminated one so we'd have a better R-squared value. The second microplate was for the green fluorescent protein assay, which just contained the 25 fractions, and Rachel will be explaining this in a future slide. We used the results from the Bradford Blue assay to make a standard curve plot. This standard curve is the standard curve plot, and the figure illustrates our standard curve and trend line, and from these data points we determined that there were inconsistencies. Rather than redoing a standard curve, we decided it was best to ensure that all the samples were created under the same conditions. This means that creating a new standard would not likely provide the most accurate comparison. Therefore, we will use another group standard curve trendline equation, and we will use this equation right here. Our data was processed using the equation, the y equals mx plus b equation, and solving for concentration. We were able to do this because of the relationship between the absorbance and concentration using the standard curve. You can relate concentration to absorbance values through Beer's law, but this would require knowing the extinction coefficient for the substance of interest, and we do not know the extinction coefficient. So in this table, fractions 21 to 24 illustrate a maximum absorbance for Kamasi blue. So this means it shows that there's protein in these fractions. Another fraction that may contain protein is fraction 4, but is most likely contaminants. One factor we have to consider is overloading the column. So this would allow for excess GFP to flow through the column, which gives us peaks at early fractions. Another factor we must consider is the role of protease. This enzyme has the potential to cut the his tag of MGH, which results in just Mg, which does not have an affinity for column. Therefore, Mg flows through the column. And then also in the table, nothing 1, 2, 3, 5 through 20, and 25 mean that there is no protein present in those fractions.
From our double y-axis plot, we are comparing absorbances at 595 and 491 nanometers. These wavelengths are for Kamasi blue and GFP respectively. Once the standard curve and calculations were completed, a double Y plot was created to show both the crude protein and the MGH. The graph on the left is using our original data, and the one on the right is another group's data. We had to use another group since ours showed inconsistencies. Both graphs plot absorbance as a function of fraction number, and the purpose of this graph is to help us determine which fractions to save and pool. Previously, Carmela discussed the standard curve plot. This plot was used to calculate the values in this table. The slope of the trend line was used to solve for the relative concentration represented by the variable x. Then we calculated the absolute concentration so we could calculate the absolute amount. The absolute amount tells us how much protein is in that specific fraction. And lastly, the total amount and the pooled fraction amount was used to find the percent yield. And after analyzing our data, we think that the SDS page team should analyze fractions 21 to 24.